Most developers think testing is something you do at the end, just to make sure nothing is broken. But in real-world systems, testing is not a single step. It's a layered safety net that protects your application from failure, performance issues, and even security risks. Because here's the reality. Your code might work perfectly in development, but fail completely in production when real users, real data, and real traffic hit it. So instead of looking at testing as definitions, let's walk through how testing actually happens in a real system, step by step, from the moment code is deployed all the way to making sure it survives real-world conditions. It all starts with something very simple, smoke testing. Imagine you've just deployed a new version of your API. Before doing any deep validation, you just want to confirm that the system is alive. Smoke testing is exactly that, a quick check to ensure nothing is fundamentally broken. You might hit a health endpoint, call a basic API, or check if the service responds at all. For example, if your login API doesn't respond after deployment, there's no point running deeper tests. Smoke testing answers a very basic but critical question: does the system even run? In real-world CI/CD pipelines, smoke tests are often automated and run immediately after deployment to catch major failures early. Once you confirm the system is up and running, the next step is functional testing. This is where you validate whether the application behaves exactly as expected based on business requirements. You define inputs, expected outputs, and compare them with actual results. For example, if a user registration API is supposed to create a new user, you test whether the user is actually created, whether all required fields are stored correctly, and whether validations like email format or password strength are enforced. Functional testing also includes edge cases. What happens if inputs are missing, invalid, or unexpected? This is where you ensure your application logic is correct and aligned with requirements. Now, even if individual components work correctly, real-world systems are made of multiple interconnected parts. That's where integration testing becomes critical. Integration testing focuses on how different components interact with each other. For example, when a user places an order, the system might call multiple services: inventory, payment, and notification systems. Even if each of these services works individually, issues can occur when they are connected. Maybe the payment service responds slowly, or the inventory update fails due to a mismatch in data format. Integration testing ensures that data flows correctly between systems and that the entire workflow behaves as expected. This is especially important in microservices architectures, where services are loosely coupled but highly dependent on each other. At this point, your backend logic might be working perfectly, but the user experience could still fail. That's where UI testing comes in. UI testing validates how users interact with your application from a front-end perspective. It ensures that buttons, forms, and navigation work correctly and that they properly communicate with backend APIs. For example, when a user clicks Submit on a sign-up form, does it correctly call the API and display success or error messages? UI testing also checks responsiveness, layout, and usability. In real-world applications, tools automate UI testing by simulating user actions like clicks, typing, and navigation to ensure a seamless experience.
Now comes one of the most important questions. Can your system handle real traffic? This is where load testing plays a key role. Load testing simulates expected user traffic to evaluate system performance under normal conditions. For example, if your application is expected to handle 10,000 users per day, load testing simulates that traffic and measures response times, throughput, and system stability. It helps identify bottlenecks, such as slow database queries, inefficient APIs, or resource limitations. Tools like JMeter or Locust are often used to generate realistic traffic patterns. The goal here is not to break the system, but to ensure it performs reliably under expected usage. But real-world systems don't always operate under predictable conditions. Traffic spikes can happen during sales, product launches, or viral events. That's where stress testing comes into the picture. Stress testing pushes your system beyond its normal limits to see how it behaves under extreme conditions. Instead of testing expected traffic, you simulate sudden spikes, maybe 5 times or 10 times the usual load. The goal is to understand the breaking point of your system. Does it crash completely, or does it degrade gracefully? Does it recover automatically once the load decreases? For example, if your e-commerce platform crashes during a flash sale, that's a critical business failure. Stress testing helps you prepare for such scenarios and design systems that can handle unexpected demand. Finally, even if your system is functional, scalable, and stable, there's one more critical dimension: security. Security testing ensures your application is protected against vulnerabilities and malicious attacks. This includes testing for issues like unauthorized access, weak authentication, data leaks, injection attacks, and API misuse. For example, can a user access another user's data by manipulating a request? Can someone bypass authentication? Can inputs be used to execute harmful queries? Security testing often includes penetration testing, vulnerability scanning, and compliance checks. In today's world, where data breaches can have serious consequences, security testing is not optional, it's essential. When you step back and look at all these testing types together, you realize something important. Testing is not a single activity, it's a progression. You start by checking if the system is alive. Then you verify if it works correctly. Then you ensure different components work together. Then you validate the user experience. Then you test performance under expected load. Then you push the system beyond its limits. And finally, you make sure it is secure. In real-world engineering, failures don't usually happen because of one big issue. They happen because one of these layers was skipped. Maybe the system worked perfectly in development, but failed under load. Maybe everything scaled fine, but had a security vulnerability. Or maybe the backend was correct, but the UI didn't handle errors properly. That's why testing is not just about finding bugs. It's about building confidence that your system will work under real-world conditions. And once you start thinking about testing this way, it stops being something you have to do and becomes one of the most important parts of building reliable software.